what I'm going to show you is one of those geometry problems where there is not the right angle inside. Things are quite curvy, lots of circles, and yet it's going to boil down to a Pythagorean theorem, which might be surprising at first. Also, this is a good example for how problems sometimes boil down to a quadratic system of equations. So with this type of geometry problems, it's very important that you draw a good picture. Don't expect to get it right away, but try until you get a good picture. Because once you have it, you're halfway through solving the problem because you understand the connections between those objects in the problem. So we have three spheres that are touching each other, and the two big ones, their radii are given, and we have to find a third one. So let's see. Here is the ground. Here is a sphere. Here's another one. And here is the third one. We can imagine that we're looking from this side, and then that cross section is the same as three circles tangents to each other. Okay, so what were the facts about tangent lines? Oh, sorry. So we want to find x, which is the radius of this tiny little circle, and we know that these other two radii are 1 and 4. And we should expect a number for x smaller than 1. All right, so what do we know about tangent lines? With a circle, the tangent line is perpendicular to the radius that is drawn to the point of tangency. And in case of circles, if you connect their centers, that line segment will include the point of tangency. So what's going on here is that all three circles, to all three circles, this line is a tangent line. So the only way we can use that is drawing these perpendicular radii. These are parallel because they're perpendicular to the same line. And then how can we use the fact that these three circles are mutually externally tangent pairwise? Well, connect their centers and the point of tangency is right there on that line. So the first thing I want to do is to avoid cluttering this picture that is fairly nice. I'm going to draw a new one. I need another one. And that's just about the two big circles. I'm not even going to include the little one. So the two circles are tangent to each other. So the point of tangency is on the line connecting the centers. And both lines are, and the tangent line, and this line is a tangent to both. So these are perpendicular lines. We have a little trapezoid, but we're going to have a right triangle really quickly, like so. Okay, so what do we know? This line here is 1 long because the radius of this circle was 1. This line here is 4 long. See, this is a badly scaled picture. This looks barely like 2. It's barely, it should be 4 times this. I just wasn't sure I could fit, but the picture is distorted. If the whole thing is 4 and this one is 1, then this is 3. And the hypotenuse, that's interesting. We just lay down 2 radii. So this is 1, this is 4. So what we have here is a right triangle with one side 3 and the hypotenuse 5, and that's the 3, 4, 5 triangle. We can run the Pythagorean theorem, x squared plus, d squared plus, I don't want to use x because I want to reserve x for what we're looking for. 3 squared equals 5 squared. So d squared is 25 minus 9, which is 16. So Or if you see 3 and 5 and make sure 5 is the hypotenuse, then it's the famous 3, 4, 5 triangle. Just to make a comment here, this equation, this quadratic equation has two solutions, 4 and -4. And this arrow here is short for, yeah, but we rule out the negative ones because they should be a distance. Okay, so now we're going to go back to the, so this here is 4. That's what we found out. If we go back to the original picture, this distance here is 4. That's what we figured out. We use this right triangle. I don't want to draw in that line because I don't want to mess up the picture. Okay. So now we're going to look at two right triangles. This is going to be one here. And this is going to be the other one. Okay. And so there are going to be two unknowns. One of the unknowns is already, we selected X. The other unknown is going to be this line segment here, Y. And then if you want to call this line segment Z, well, Y plus Z is 4. Therefore, does it fit? Therefore, Z is 4 minus Y. So I don't want to have three unknowns. So so if this is Y, it's here, this is going to be 4 minus Y. Okay. Now this line segment here is X, and it's X everywhere, right? And then this is the radius. This here is the radius of the circle. That's 1. So what we have up here, that is 1 minus X. And that might feel a little frightening, like, wait a minute, 1 minus X, that could be negative. But if you recall, X should be less than 1. So this expression makes sense. Okay. Now, this side here is, again, one radius, 2 radii. So it's X, so the hypotenuse is 1 plus X, right? This is 1, this is X. And then the horizontal side is Y. So the first equation, the Pythagorean theorem stated for this triangle is Y squared plus 1 minus X squared equals to 1 plus X squared. And if you have been doing algebra, you can probably anticipate that there is going to be some cancellations. So before we find the second equation, let's simplify this one. Y squared plus 1 squared is 1 minus 2x plus x squared. And then on the other side, we have 1 plus 2x plus x squared. But 1 definitely cancels out and x squared definitely cancels out. So what we're left is y squared minus 2x. Let's add that 2x to the other side. So we get y squared equals 4x. That's not bad. Yeah, it's quadratic, but among quadratic equations, this is pretty much as good as it gets. Let's hope for something nice for the second equation, which we're going to get by expressing the Pythagorean theorem stated for this triangle. So the horizontal side is 4 minus y. The vertical side, well, this whole thing is 4 and this is x. So it's 4 minus x. And the hypotenuse is 4 plus x. This is x, this is 4. So it's 4 plus x. So 4 minus y squared plus, so 4 minus y squared plus 4 minus x squared equals to 4 plus x squared. And again, there's going to be some nice cancellations here. So we have 16 minus 8y plus y squared plus 16 minus 8x plus x squared equals to 16 plus 8x plus x squared. 16 cancels, x squared cancels. And then there's a minus 8x here and a plus 8x. Let's add 8x to the other side. Then we're left with y squared minus 8y plus 16 equals to 16x. So now the question is, okay, so here is the system. What do we solve for? What do we substitute? And I think the easiest way is we can get rid of x, even though that's the thing we ultimately look for. I think we're much better off if we solve first for y after we eliminate x. We're not going to use elimination. Check this out. 16x is just 4 times 4x. That's 4y squared. So if you rewrite y squared minus 8y plus 16 equals 4y squared, x is gone. So let's solve. This is just a quadratic equation in y. Let's solve it. I'm going to use the quadratic formula. We have 3y squared plus 8y minus 16. So we have negative 8 plus minus square root of that's always encouraging. So we have negative 8 plus minus 16 divided by 6. When we use the minus, we get clearly a negative number. So that's the one we are not interested in because x and y both are distances. So let's get that out of the way. Negative 4, that one is ruled out. And then the other one that's going to be hopefully the solution is negative 8 plus 16. That's 8 over 6. That's just 4 over 3, isn't it? So if y is 4 over 3, I think we can get x from here quickest. Then x is y squared over 4. And y squared is 16 over 9. And to divide by 4 is the same as multiplying by the reciprocal. That's 1 over 4. So what we get is 4 over 9. Which indeed is less than 1 as we expected. It's almost half, right? 4 over 9 is almost 4.5 over 9. So it's a little bit less than half. So that's how you do that. Don't expect to get the pictures right away. You have to sit there and draw a lot of lines this way, that way, until you stumble into the correct solution. Thank you for watching.